Okay, in this video I'm going to provide a general demonstration of binary logistic regression using SPSS's mixed models procedure. So essentially what we're going to be doing is going through the generalized linear modeling option and running an HLM with a dichotomous outcome variable. So essentially this translates into a multi-level binary logistic regression. So basically with logistic regression, most of the time this type of analysis is carried out on data that are assumed to all be at a single level. And the dependent variable is essentially dichotomous, and it represents group membership. So typically you have a baseline or a reference category or group, and then you have a target group. And so the idea is, in the context of standard logistic regression, the idea is to develop and test models predicting the likelihood of target group membership as opposed to the baseline group as a function of a set of predictor variables. So the same general logic applies in the context of a multi-level binary logistic regression, but things get a little bit more complicated just because of the multi-level nature of the data. So with multi-level binary logistic regression, the basic idea is that we are still modeling relationships between predictors and a dichotomous outcome, but those relationships might vary between different level 2 or level 3 units, just depending on the grouping structure in your data. So what I have right here is a data set, and this data was actually taken from an example that was provided in Chapter 9 of David McKinnon's book, Introduction to Statistical Mediation Analysis. And in that particular demonstration, he was actually demonstrating multi-level mediation. But I thought this would be pretty handy just to kind of use in this current example. So we're just kind of modifying the general approach to analysis in order to demonstrate the multi-level logistic regression. So in the example that he provided, what he had was essentially simulated data from about 112 individuals, and those individuals were nested within basically one of 16 therapy groups. And the therapy groups were randomly assigned to either a cognitive behavioral treatment program or a cognitive behavioral plus exercise program. So essentially the treatment variable is associated with each group. So you'll see right here we've got group 1. Those individuals were assigned to treatment group 1, and this would be the cognitive behavioral program plus the exercise program. Group 2 was assigned to just the standard cognitive behavioral intervention and so forth. So essentially then we have the individuals who are nested within different treatment groups, and treatment group was associated or randomly assigned, or the individual therapy groups are randomly assigned to either being the treatment or the control condition. So the individual level 1 outcome variables included a measure of fitness and a measure of happiness, and happiness was the outcome measure. So the idea was that these individuals were being measured. The level 1 outcome variable was happiness, and it was assumed to be a continuous measure. And the mediator in that previous McKinnon's model was fitness, and so the idea is that being assigned to either the treatment or control group, that the effect of the treatment condition on happiness might be mediated through fitness. So again, we're not really doing that in this case. We're just going to use treatment in the current examples as essentially a level 2 predictor of the variation in intercepts, and we'll use fitness as a level 1 predictor of happiness. Because happiness was originally a continuous measure, what I did was I dichotomized that variable. Typically, you would not want to do this. This is not a good approach to analyzing data by taking a continuous measure and sort of chopping it up and forming dichotomies. Essentially, you're reducing the variation that was available in the original measure to essentially 2 levels for this variable. So just kind of keep that in mind. Nevertheless, this is just a demonstration of the process of multi-level modeling with the dichotomous outcome. So we're just gonna stick with this variable here as our outcome variable at level 1. So you'll notice that we have codes of 0 and 1. So basically 0 would be the low happiness group, the 1s would be the higher happiness groups. So in other words, individuals who were coded 0 after the treatment program, we would assume that those people were less happy. People who are coded 1 would be more happy. So if I was going to run a standard binary logistic regression all at level 1, I would basically be going, there are actually a couple of routes in SPSS. I could go through the regression route, go to binary logistic regression. I would just be using my dichotomous outcome variable, place that in the dependent box. I'd be placing fitness here. Now, as I said before, the data is actually nested, or the individual data is nested within different treatment groups. So ordinarily, this would not be a strategy to kind of adopt here, but I'm just going to demonstrate what the logistic regression would look like at level 1 and just kind of ignore the clustered nature of our data. So you'll notice that when you're running these analyses or the analysis at level 1, basically what you'll end up with is in terms of the output, you'll end up with you'll get kind of a general overall model fit. You can evaluate that using sort of the chi-square test right here, and you can see it's statistically significant. What this is telling us is that the model that includes our predictor variables represents a significant improvement in fit over a null model that includes no predictors. So that's kind of that's one way to assess fit. We also have down here, you can see we've got some pseudo R-square statistics that can be used sort of as a descriptive way of judging fit of the model to the data. There's another test right here. This is a Hosmer-Lehman-Show test. If this is non-significant, that actually indicates good fit to the data. And then you also have some other indices. You got a classification table, which essentially what you have is sort of looking at the correspondence between the values that were observed in the data and those that were predicted by the model. So right here you've got those cases that were observed to be the low happiness cases. These are the predicted happiness or low happiness individuals based on the model. You had a correspondence of 40, 40 out of basically 53 individuals were correctly predicted to fall into the low happiness category for an accuracy rate of about 76%. You have essentially out of 59 cases, you had 48 correctly classified into the happiness group, or predicted to be in the happy group, and with an accuracy rate of about 81%. So the total accuracy rate for the model was about 78.6%. So it's pretty good classification accuracy. Then down here you can see in terms of the regression coefficients, you'll see that fitness, this is a positive coefficient, and essentially the regression coefficient pertains to the predicted change in log odds associated with a 1 unit increment on a predictor variable. So I'm not going to get too far into the issue of log odds, but you can roughly think about that in terms of as the log odds are increasing, that means that there's a greater likelihood or probability of falling into the target group relative to the baseline group. So the fact that this coefficient is positive is indicating that as scores on fitness are increasing, there's an increasing likelihood of falling into the happy group as opposed to the low happy group. You can see that predictor was statistically significant. And then this is an odds ratio, and this is essentially kind of pivoting off of the information from the log odds, and it's essentially reflecting a ratio of, this is reflecting changes in the ratio of the probability of falling into the target group to the probability of falling into the non-target group or the baseline group. So, essentially this is what is referred to as odds, and this index right here is discussing how the are utilized to indicate the changes in odds for every unit increment on the predictor variable. So basically a value of 1 indicates that the probability of falling into the target group is equal to the probability of falling into the baseline category. And so a value that is greater than 1 is going to indicate that there's a greater probability of falling into the target group as opposed to the baseline group. A value that is less than 1 will indicate that there's actually less of a probability of falling into the target group relative to the baseline group. So that's kind of roughly how to talk about this. I can't really go into a lot of details, or else this will take forever for the video. But then we have a treatment. You can see that it's positive. And the coding on this was essentially a code of 0 represented the just the standard cognitive behavioral group, the 1 representing the cognitive behavioral plus special exercise condition. So you can see that was statistically significant, and you have a much larger odds ratio here. So there you go. So as I said, basically because our data are clustered within groups, and it kind of begs the need for a multi-level analysis. And so to do this using SPSS, what we're going to do, I'm just going to go back to the data set here, and I'm going to go to Analyze, Mixed Models, and then go to Generalized Linear. So in this particular case, now when this box opens up, what you'll want to do is you'll want to move your grouping variable. We're only going to be using 2 levels. So level 2 is the therapy group. So we're going to use that in the subjects box. So this is basically indicating this is sort of the level 2 grouping structure. So I just was being very nondescript and called it group. All right, so at this point, we've identified our level 2 identifier variable, which is our group variable. Next, we'll go to Fields and Effects. And now you'll see this box right here. It says Target. So I'm just going to click on this and then find my outcome variable. So it's going to be this happy. I just have DVAR for essentially reflecting as the fact that it's a dummy variable. So I'm going to click on that, and so now you'll notice that it changes from use predefined target to use custom target, and so now we have to specify the target distribution and relationship, the link function. So we're going to click on Binary Logistic Regression, and now what we need to do is to specify our fixed effects for the model, and we'll start off with just an intercept only model, and then we'll move to incorporating our predictor variables. So for the intercept only model, essentially there will be no predictors. You'll see that right now it's defaulting with intercept. If I clicked off of this, I would get no intercept. So in other words, the intercepts would not be randomly varying between groups, and I don't want to do that. I want to keep the random component for the intercept in the model. Next, I'll click on Random Effects and click on Add Block. So when this box comes up here, then there are several things to kind of note. First of all, I want the intercept to randomly vary across groups, so I'm going to click on Include Intercept. And so that's what this is doing under the random effect blocks. Under subject combination, I'm going to click on this box and go to group, which is my variable that is identifying the level 2 units, basically the therapy groups. I have option in terms of the random effect covariance type. So you'll notice basically this is the options here are the same that are available to you using the standard mixed models approach in SPSS. So we got variance component. Essentially what that's going to do is it's going to estimate, because we only have the intercept in the model, it's only going to estimate the variance of the intercept and allow us to test for statistical significance. One of the things to note, unlike standard mixed models with a continuous outcome, is that in our case right here, we're not going to have a level 1 residual. So the only variance component that's going to be estimated is going to be at level 2, and that is going to be the variance of the intercepts. So now what I'll do is I will click on OK. And so now you can see intercept. It says yes right here. Under fixed effects, you see again, we have the intercept right here, and so forth. Under build options, a couple of things to note. In the program, if you happen to have your variables, like we have our outcome variable specified here as essentially I think it's laid out as a nominal variable. And then we have treatment, which is also being treated as nominal variable. So what's going to happen is that the program is going to recognize these as nominal variables and treat them as essentially as factors. So when this is the case, we want to go to sorting order, and typically we use the group that is coded 0 as sort of a baseline group or a reference group, and then the group coded 1 as being the target. So what we're going to do is we are actually going to go to sorting order, and I'm just going to click on descending for both of these. And it will just make life a lot easier when it comes to interpreting the regression coefficients, because the reference category otherwise would be the target group as opposed to the non-target group. So if we left it the other way, so we don't want to do that. Down here you've got some options in terms of tests of fixed effects and coefficients. And we'll just stick with the assumed model assumptions are correct, but theoretically we could click on robust estimation if we thought that there were violations of model assumptions and so forth. Under estimation, these are just some defaults that are available to you. Under model options, we're not going to really bother with anything there. So we've laid out an intercept only model, and so I'll click on run. And so now what you'll see in terms of the output, you'll see we've got our model summary table. You can see the total N was 112. The number of groups was the 16 right here, and so forth. You'll notice that the probability distribution is a binomial distribution. The length function is logit. And then we've got a little bit below, you can see we have classification table. So you can see right here, this is interpreted very similar, very much the same way that we interpreted the classification table with the single level approach to logistic regression. So you can see the observed, which is the observed being one being happy group or a high happy group, 0 being the low happy group. And so you have essentially the correspondence in terms of the counts, and then the percentage of correct classifications. And so you can see right here that we had essentially 50 individuals out of 59 were correctly predicted by the model to to fall into the high happiness group. The accuracy rate was about 85%. When it comes to the low happiness group, you can see right here 40 out of 53 were correctly classified or predicted by the model to fall into that category. So for an accuracy rate of about 75.5%. So the model's doing a pretty good job here. Now when we scroll down under fixed coefficients, you can see we've got the intercept, which would be, essentially the average probability, essentially an average intercept across the groups. You'll notice that in SPSS you'll get some of these kinds of tables. I guess in newer versions, I'm not a big fan of these, but if you click on this, I guess you could theoretically, you could actually theoretically, make edits and so forth, but like I said, I'm not a big fan of that. Going down below, you've got the random effect covariances and so forth. You'll see that the residual effect at level 1, you'll see there's essentially nothing here, and that's reflecting the fact that there's no level 1 residual when you don't have a continuous outcome measure. So you're not going to be interpreting this. So, but if we want to interpret the variation in the intercepts, this is the intercept variance right here, the z-value and a significance level. This is a walled z-test, and my reading on this is that basically this is a p-value for a two-tailed test, and given that a variance cannot be negative value, really what you ought to be doing is essentially splitting this p-value in half, and that'll get you a corrected p-value for a one-tailed test. So the p-value for the random intercept is about 0.03. So there's evidence of significant variation in the intercepts across the groups. Okay, so let's do one other thing to kind of note too is if it happens to be the case, sometimes there are other options in terms of the output display, and so sometimes if you're running your analysis, you might end up with a different type of display. I'm just going to show you that really quickly. If you go to Output under Options, go to Model Viewer, and then click on OK, and I'll just kind of show you the difference. If we run that model, you can see the output summary is a lot, looks a lot different. You sort of have to click through a number of different boxes. It's all the same information. And you can get various diagrams and tables and so forth. I really am not a big fan of this particular approach, but I want you to know that it is there, and that if you happen to have run your analysis and it looks like this, no, you did not mess anything up. It's just a difference in terms of the output that you've requested. So I'm going to go back really quickly to go back and reset this. You'll notice it says output display method applies to generalized linear mixed models and and non-parametric tests. So this is what we're working on right now, the generalized linear mixed models. So I'm going to go back to pivot tables and charts because I tend to like that a lot better. Okay, so next, let's add in a level 1 predictor. So let's add fitness in as a predictor. So we're going to use that at level 1. And then let's also add in treatment as a level 2 predictor of the variation in intercepts. So we're going to go to Mixed Models, Generalized Linear, and go to Fixed Effects. And so now you'll see, under Fixed Effects right here, we're going to move. Now, the way that you do this is you just simply, pick your variables and move them over. So I'm just going to click on this and drag it over to the main for main effect, and then click on this variable right here and drag it over as well to main as well. So now I've got essentially my level 1 predictor fitness and level 2 predictor treatment. So I'm going to leave everything else the way it was. I'm not going to ask for randomly varying slopes or anything like that for the level 1 predictor. I'm just going to stick with these effects as being fixed and just still allow the intercept, basically to randomly vary across the groups. So I'm going to click on Run. And so now when we look at our model, you can see that we have, in terms of our classification accuracy, you can actually see we're about the same in terms of predicting folks that fell into the happy group, but we've done a better job of predicting the folks that tended to fall into the low happiness category. So, really looks like we've kind of added some predictive power in terms of predicting category membership. Now, again, under fixed effects, you sort of have several pieces of information. This is just sort of a general test of the fixed effects of fitness at level 1 and treatment at level 2. This box right here, you can see that gives you sort of a pictorial representation of the effects of these variables here. Like I said, I'm not a big fan of these kinds of deals here, but I'm going to go down to my little table here for fixed coefficients. And you can see right here that fitness, so now in terms of the coefficient, this again is referring to the predicted change in log odds of membership in the target group for every increment or 1 unit increment on the predictor variable. So you can see we have a positive value here, again reflecting the idea that higher fitness levels are associated with higher probability of falling into the higher happiness group. You can also see we have the odds ratio right here, which is positive, which also is going to be essentially reflecting the idea that, again, the probability of falling into the target group, or I guess you could say the high happy group, is greater than the probability of, falling into the low happiness group. But now again, the odds ratio is really reflecting the change in odds. So so just kind of keep that in mind too. That essentially this is the changes in the odds for every increment on fitness. So in other words, because this is a positive value, then this ratio is increasing at higher levels of fitness, and then as at lower levels of fitness, this ratio is actually decreasing. So that's the way to think about it. The treatment categories, you can see we've got treatment 1 and treatment group 0. Because the program is perceiving these treatment variable as nominal, it's essentially it's giving you the regression coefficient for the treatment variable, and essentially it's kind of reflecting this is really a difference in terms of the predicted log odds between the group coded 0, the standard cognitive behavioral group, versus the group coded 1, which is the cognitive behavioral plus exercise. And so you can see right here that that the difference between the groups in terms of the log odds or predicted log odds was not statistically significant. So it appears that treatment at level 2 was not a significant predictor of the probabilities associated with being in the high happy versus the low happy groups. So at any rate, let's scroll down a little bit more so you can kind of see the fixed coefficients, and it's giving you sort of the positive, this is the positive coefficient, this is a negative coefficient, so there you go. Scrolling down a little bit further, you can see that when we added in the treatment variable, the variance in the intercepts actually dropped to non-significant. So that's essentially the effect of adding in the treatment predictor at level 2 of the variation and intercepts across the groups. Again, we're not going to be interpreting the residual effect at level 1 because there's not going to be level 1 residuals. So the other thing to kind of note is that if let's say we converted our treatment variable to a we could use this as a scale variable since it is a dummy coded variable. And so if we do that, then if we run our analysis right here, you can see fitness is treatment is already kind of filled in as a scale variable in SPSS. So when it comes to looking at the build options, then you'll notice that essentially it says the sorting order of categorical targets versus predictors. So really, it's not going to matter right here because the program's going to recognize treatment as a scale variable. And it's not going to change the estimates or anything of that nature, but it'll look a shade different in terms of some of the presentation, or just a whisper of a difference. So you'll notice down here in terms of the fixed coefficients table, you'll see the treatment, and you can see this is the regression coefficient, and you can see the significance level. So these values are exactly the same as what we had above when we ran the analysis, but the program was recognizing treatment as a nominal variable. So that's just a little bit of a difference. I tend to prefer this approach, and it also saves you the hassle of having to reset the variable as essentially using the descending order or whatever. So all the results, though, are exactly the same. So this was, like I said, this was intended to be sort of a quick overview of, essentially a multi-level binary logistic regression. It's certainly not exhaustive. There's a lot more that can be said and done with this, but this was just to show you how you can carry out some of these analyses using SPSS. So thanks for watching.